Gauss theorem is always valid, but only useful for symmetrical cases. Gauss theorem is always valid, but useful only for symmetrical cases. I'll tell you what it means by some examples. Gauss theorem is always valid, but only useful for finding electric field when symmetry exists. When symmetry exists. And we'll use this to find the flux due to different scenarios. Do you remember we had discussed the electric field due to a point charge and we solved it using Gauss theorem? In the previous class, we proved that electric field due to a point charge. Shall we do it again, or is that clear to you? Rishit, do you remember the last class?
No, sir.
Okay. Okay, let us go through this whole thing again. So first thing, using the Gauss theorem, we will deduce electric field due to a point charge. Electric field due to a point charge. Now, Gauss theorem is a powerful tool, but you have to be smart about how you choose the Gaussian surface. So I have a point charge here Q, and I want the Gaussian surface to be symmetrical. So I will choose the Gaussian surface to be a sphere. This is a spherical Gaussian surface. And let us say we don't know the value of electric field due to a point charge. And we're going to find it using the Gauss theorem. But we know as all the points on the surface, they are equidistant from the center. Let's call this distance as R. And let us take this area as ds. And electric field will be in the radially outward direction at this point. This much we can guess. Now, I'll write the Gauss law, that is summation of E dot ds will be Q by epsilon naught. So electric field, suppose we don't know, but what we know is that electric field at each and every point on the Gaussian surface will be same, because each and every point is the same distance away from the charge. And one thing we know, distance between the angle between the electric field and the Gauss and this small surface on this small surface is 0. So dot product can be written like this, that is E ds cos 0 degree. The ds vector is in the same direction as the electric field vector. So this is Q by epsilon naught. Then we have cos 0 is 1. So I have E into ds. Now, E is a constant because it is the same everywhere on the surface of the Gaussian sphere. Now, integration of this surface, that means total area. ds is area of the small region. So integration of this will give you area of the Gaussian surface. This summation of E dot ds, it will give you area of Gaussian surface. So we can write E into 4 pi r square is equal to q by epsilon naught. So E will be 1 by 4 pi epsilon naught q upon r square. This is the result that we get again from the Gauss law. We also got this from Coulomb's law. Are there any questions about this? Apura, is this clear?
Yes, sir.
Okay. So see, Gauss theorem here was valid, but it was made useful only if the Gaussian surface is symmetrical about the charge. Suppose the charge was here, but you had taken Gaussian surface here somewhere. So it would not have been useful because electric field at each and every point would have been a different value. And it was impossible for us to integrate manually. So that was the first example. Second, we are going to take electric field due to a line charge.
Could you please scroll up?
Okay, you want to note it down?
Yes.
Yeah.
Noted.
Okay. Now see, electric field varies as 1 upon r square. So we can draw this graph. As the value of r increases, the value of electric field will decrease continuously. Now, next we are going to find electric field due to a line charge. And due to an infinite line charge. We call it infinite, but a very long wire would also do. So it is drawn like this. So this wire is very long, and this line charge is really long, and it has positive charge distributed over it. Because the charge distribution is linear, we'll call this to have a linear charge distribution. And so we'll say that lambda for this is constant. Lambda is called linear charge density or charge per unit length. Charge per unit length remains constant. Now, if I try to draw the Gaussian surface for this, so it will be smart if we draw a cylinder. If I draw a cylinder, let us see how it will help us. This is our Gaussian surface. And if I draw the electric field lines, the electric field lines will be radially outwards, like this. On this side, it will be radially outwards like this. And see, this is a Gaussian surface, no? So it's a whole cylinder. So a cylinder has three surfaces. First is the curved surface, then the top lid and the bottom lid. On the top lid, electric field will just go along the plane. So we have three regions to calculate the flux. First, I have to also write the dimensions of this. Let us say the radius is r. and the length of the cylinder, call it L. So of course it looks like that electric field should only vary with R or should only depend on L. Let us see if it varies with R or it varies with L. If I try to write the Gauss law, I will write summation of E dot dx, E dot ds will be equal to Q by epsilon naught. Or I can also write it like this, that total flux is equal to Q inside by epsilon naught. Now see, flux through the cylinder, this is flux through the cylinder. Flux through cylinder will depend on three fluxes. Flux through this curved surface. Let me call this as flux through the curved surface. Then flux through lid 1 and flux through lid 2. Or I can just write it as phi 1, phi 2, phi 3.
And
Where?
what is phi 1, phi 2, phi 3?
Phi 1 is flux due to the curved surface. Phi 2 is flux due to the lid, upper lid, top lid. And phi 3 is flux due to the bottom lid. And charge inside, see, lambda is charge per unit length. So I can write lambda as Q by length of the cylinder. Charge inside will be Q inside by L. From here, we can write the charge inside is lambda times L. So phi 1 plus phi 2 plus phi 3 is equal to lambda times L. This comes from your Gauss law. Any questions up to here? Okay. Now see, if I calculate flux due to the first region, we know that electric field at each and every point on this curved surface will be the same. If I draw a surface ds like this is your ds vector and this is your E vector. So flux will be summation of E dot ds. See, I'm not drawing a closed region because this is not closed region. The curved surface is not closed. So E dot ds will be again E ds cos 0. E is a constant, so it will go outside. That will give me E into ds. Now, what is curved? What is integration of ds? Integration of ds for this, for the first region, will be surface area of this, curved surface area of the cylinder. This should give you curved surface area of the cylinder. And curved surface of area of the cylinder is 2 pi r L. So this is the flux due to the first curved surface. Similarly, we can find flux due to the second curved surface. The top lid. Now see, we can write this as E dot ds again for the second surface. And see, for the second surface, electric field is like this. But if you draw a small surface here, or if you draw a small surface here, the ds vector is perpendicular to E vector. So E dot ds, the angle between them is 90 degrees. Electric field is along the line, along the plane, and ds vector is perpendicular to the plane. That means the angle between E and ds is 90. So here you will write E ds cos 90. That will be 0. And same goes for bottom lid. For bottom lid also, electric field is radially outwards But if you draw your Gauss small surface here, it has a direction away from the plane. This is your E vector, this is your ds vector, angle between them is 90 degree. So E dot ds will give you 90 degree. So if E dot ds is 90 degree, then your net flux is 0. So for the bottom lid also, the net flux comes out to be 0. Because angle between the area vector and electric field is 90 degree. So if you write the net flux is equal to phi1 plus phi2 plus phi3. This gives you lambda L. And phi1 is, you can write phi1 from here. Value of phi1 is E into 2 pi RL. So this will be E into 2 pi RL. Phi2 will be 0, phi3 will be 0. That is equal to lambda times L. From here, you get the value of electric field as lambda L upon 2 pi RL. Lambda and lambda will get cancelled. L and L will get cancelled. And this will be lambda upon 2 pi R. You're missing epsilon naught here. It should be Q by epsilon naught. So lambda L by epsilon naught. Here it should be epsilon naught. So here it will be epsilon naught. And this will be corrected as lambda by 2 pi epsilon naught R. So this does not varies as R squared. This varies as 1 by R. Electric field is proportional to 1 by R. If I draw a graph between the electric field and the distance from the linear charge, so this will vary as R increases, electric field will decrease. The graph will be like this. Okay, any questions?
Sir, I didn't understood the last equation is equal to lambda by 2 pi epsilon naught R.
The last equation comes from here. Means phi is lambda L by epsilon naught. Flux due to 1, that is E into 2 pi RL. Flux due to 2 is 0. Flux due to 3 is 0. Is that clear? This line clear?
Yes, sir.
Okay. Then I have just to put this 2 pi RL here in the denominator. So lambda L by epsilon naught and 2 pi RL goes on this side.
Yes, sir, understood.
Okay. Note this down.
Sir, could you scroll up?
Previous page. Okay. So here we are talking about electric field due to an infinite plane sheet of charge, and we're drawn the infinite plane sheet, and the surface charge density is sigma, and sigma is given as a constant. To find out the electric field, we have drawn the surface like this, and the Gaussian surface is a cylinder. I'm zooming in the cylinder. We have three surfaces: first surface, second surface, and the third surface. First surface is the curved surface. If I draw the electric field line, let us say the charge enclosed is this, positive charge is enclosed over this, like this, and electric field will be radially outwards. It will be away from the charge. Now, on the curved surface, if you observe, on the curved surface, it is along the surface. And on the curved surface, if you draw a ds, it will be like this. If you draw ds, it will be like this. Ds vector will be like this. But your electric field is away. Electric field is away. So I'll calculate flux due to the first portion first. So flux due to the first portion That will be integration of E dot ds. For the first surface, the angle between the ds vector and E vector is 90 degree. So it will be E ds cos 90. It again becomes 0. So flux to the first surface becomes 0. Then let us calculate the flux due to second surface. For the second surface, you will draw a ds vector and the electric field is along the ds vector. This will be again E dot ds. This was for first, this was for the second surface. EDS cos 0 degree. This will be E into ds. Now, area of the second surface is given as A. So this will be E times A. Similarly, you can calculate the area for the flux for this third surface. If you calculate again, the third surface electric field and ds are in the same direction. So you'll again get A, E into A. Now you can calculate the total flux. Total flux is given by the charge inside by epsilon naught. This is from Gauss law. This is from your Gauss law. And I will put the value. Total flux will be equal to flux through surface 1 plus flux through surface 2 plus flux through surface 3. That will be Q by epsilon naught. Now see, surface charge density is sigma. If surface charge density is sigma, that means sigma will be equal to charge on this region divided by area of this region. Area of this cross section was A. So sigma will be charge per unit area. From here, you can write your charge as sigma times area. So here I can write charge as sigma times the area. Flux due to 1 is 0. Flux due to 2 is E times A. Flux due to third surface is also E times A. This is sigma A by epsilon naught. And from here, if you calculate the value, your E will be sigma by 2 epsilon naught. And that is the answer. You see, it is independent of the distance. It is independent of the distance. This electric field remains constant around the infinite plane sheet of charge. Any questions? Now, this was due to a single plane sheet of charge. Now, for a single plane sheet of charge, suppose it is positively charged and you want to find this is infinite plane sheet. This is infinite plane sheet with a surface charge density, let us call it sigma 1. So it will have electric field. Let us say at this point, if you want to find the electric field, it will be sigma 1 by 2 epsilon naught. And at this point also, it will be away from the surface. Its value will be sigma 1 by 2 epsilon naught. Suppose there is a similar case like this, but instead of positive charges, there are negative charges.
Sir, how sigma 1 by 2 epsilon naught?
We have just derived the equation sigma by 2 epsilon naught.
Yes, sir.
Electric field is sigma by 2 epsilon naught. So here on each and every point around the surface, electric field will be sigma 1 by 2 epsilon naught. If suppose the infinite plane sheet is negatively charged, So let us say the charge density is sigma 2. In that case, you can write the electric field will be towards the surface, and its value will be sigma 2 by 2 epsilon. Okay. The only difference is that electric field is towards the charged surface. That's the only difference. And magnitude remains same, sigma 2 by 2 epsilon. Taking some more cases. Suppose I have two infinite plane sheets. They are kept side by side. First sheet is like this. If I write sigma, then you have to assume that it is a surface. And there is another plane charge sheet. This is also positively charged, but with another different surface charge density. So if I try to find electric field in this region, electric field in this region will be electric field due to the first sheet, and there will be electric field in the second due to the second sheet also will be in this direction only. So the net fields will be added. So electric field in this region will be E1 plus E2. Net electric field will be E1 plus E2. So this is E net, that is E1 plus E2. E1 will be given by sigma 1 by 2 epsilon naught. E2 is again due to this surface, sigma 2 by 2 epsilon naught. So net electric field comes out to be sigma 1 plus sigma 2 whole divided by 2 epsilon naught. That is the net electric field when the point is on the left side of both the plane sheets. Now, if you take a point here, electric field will be in the right direction due to the first sheet. This is the first sheet. This is the second sheet. Now, due to the second sheet again, electric field will be at this point again in right direction. So again, you can write the net field in this region as sum of these two, E1 plus E2. Resultant will be again sigma 1 plus sigma 2 by epsilon naught. So when point is on the right side of both these sheets, the electric field will get added. But think about this. If the point is here, then this sheet will give electric field in this direction, E1. And this sheet will give electric field in this direction. So in this region, if you want to write E net at this point, so at this point somewhere here, the net electric field will be E1 minus E2. If you write E1 minus E2, then of course, you're assuming that E net is in this direction. So in that case, E1 is sigma 1 by 2 epsilon naught. E2 is sigma 2 by 2 epsilon naught. So the net electric field will be sigma 1 minus sigma 2 by 2 epsilon naught. This is when there are several regions of several plane sheets. If there's a third sheet again, you will keep on adding and subtracting depending upon the direction of electric field. Because this electric field does not depend on the distance, as it is an infinite plane sheet, you will just add up the electric fields with their directions. Similarly, if suppose there is one positive plane sheet and another negative plane sheet, or let us take 3 plane sheets now. So I will draw it like this. The first sheet is here. This is positively charged. Let us say the value is sigma 1. Then we have a second sheet. You can call this as positively charged too. And then let us take one more sheet. This you can take it as negatively charged. And value is sigma 3. So suppose you want to find electric field, let us say in this region. And this is your first sheet, second sheet, third sheet. So first sheet will give electric field away. E1 will be in this direction. The second sheet will give electric field again away. So E2 will be in this direction. Third sheet will give electric field in the leftward direction. So in this region, you can write E net as E1 plus E2 minus E3. That will give you sigma 1 plus sigma 2 minus sigma 3 by epsilon naught. 2 epsilon naught. Okay, let us say you want to find electric field in this region. So electric field due to 1 is towards the right. Electric field due to 2 will be towards the left. And electric field due to 3, this will be again towards the right. So in this region, if you want to write E net, that will be E1 plus E3 minus E2 divided by 2 epsilon naught. Oh, not 2 epsilon naught. If you put the values, then sigma 1 plus sigma 3 minus sigma 2 divided by epsilon naught. And likewise, you can find electric field in the other two regions, here and here. Any questions over this? You can try it on your own. So in this region, I will just write the value. You can try it at home in this region. E1 will be here, E2 will be here, E3 is also in this direction. So E net will be E1 plus E2 plus E3 divided by, that will give you sigma 1 plus sigma 2 plus sigma 3 divided by 2 epsilon. If I talk about this region, E1 will be here in this direction leftwards, E2 will be also leftwards, but E3 will be towards right. So for this region, you can write in this region, the value of E net is equal to sigma 3 minus sigma 2 minus sigma 1 whole divided by 2 epsilon naught. So even if there are 3 sheets, 4 sheets, 5, 6, 7 sheets, you can just write electric field due to individual sheets and add up them like vectors. Principle of superposition will give you the net electric field. Any questions over here?
Okay.
Okay. So once these are all applications of Gauss law. Once you understand Gauss law, this results becomes very easier to calculate. And after calculating the result, this is a simple result sigma by 2 epsilon naught when a charged plane sheet is infinite and electric field is needed to be found, sigma by 2 epsilon naught. So you must also remember this result. That will help you in exam. Now after this, we will go to electric field intensity due to a conductor. Next is electric field due to a conductor. And we're going to talk about just outside a conductor, not very far away from it, just outside a conductor. So suppose you have a deformed conductor, a conductor of random shape. You can take it like this, any shape, and you give some charge over it. You give some charge over it. Of course, charge distribution will not be uniform. Some places will have more charges, some places will have lesser charges. Where there are sharp edges, the amount of charges is greater. Where there are blunt, means smooth edges, the surfaces
The
has less
charges are
charges.
evenly spread.
No, charges are not evenly spread. It depends on the shape of the conductor.
Shape, exactly, yes.
So if there is a pointy region, there the number of charges will be more. The reason for this, you'll be studying in next chapter, electric potential. Potential at each and every point on the conductor remains the same. So this is a conductor. And suppose you want to find the electric field very near to the surface. So I will draw a Gaussian surface like this. So if you zoom this out, it will look something like this. And there is a charge in this region, let us say here. And it has some surface charge density at the local point. Okay, this is local surface charge density. It will be different at each and every point. So local surface charge density. So very near to the surface, if you go very near to the surface, the electric field, you can say that it is radially away from the surface. Only if you are very near to the surface. So that's why I've written just outside, not very far away, just outside. So electric field will be like this, but inside the conductor, there is no electric field. So here and this region, there is no electric field. Electric field is zero. Okay. Inside the conductor, electric field is zero. All right. If suppose the area of this is given as dA, then electric field will be normal to this dA. The flux to the Gaussian, this cylindrical surface, you can write this as, suppose let us apply Gauss law. So you have three surfaces again. So let's call this surface as the first surface, this as the second surface, and this box as this circle as the third surface. So we can write our Gauss law. Total flux is equal to charge inside by epsilon naught. This is your Gauss law. So total flux will be flux due to 1 plus flux due to surface 2 plus flux due to surface 3. And charge here will be sigma times dA. Okay, if you want to calculate charge on this, let us call it dq. So sigma will be dq by dA. What is sigma? Sigma is local surface charge density. Local surface charge density. This is charge on this, charge enclosed. dq is charge enclosed. And dA is area of cylinder, cross-sectional area of cylinder. From here, we come to the conclusion that charge here will be dq. Charge on this region is dq. That will be given by sigma times dA. So here I can write sigma times dA by epsilon naught. Flux through surface 1, there is no electric field, so it will be 0. Flux through surface 2, electric field is along the surface, so that is also 0. Now flux through surface 3rd is E times dA. Again, dA will be, the direction of dA is along the electric field. So this is sigma dA by epsilon naught. So from here, E dA is equal to sigma dA by epsilon naught. That is, electric field is equal to sigma by epsilon naught. So see, electric field only depends on the local surface charge density. Electric field only depends on the local surface charge density. There it was sigma by 2 epsilon naught. Here it is sigma by epsilon naught. Any questions over here? Electric field due to a uniformly charged spherical shell. The spherical shell means there is just a sphere which contains the charges. So if you have a conductor, the charges like to go on the outer surface of the conductor. Of course, if it is not influenced, it should not be influenced by other electric fields and other charges. The charges, positive charges, like to make maximum distance with each other. Let us say this has a radius r, capital R, and I want to find electric field at 2 points. Let us call my first point as P here, which is small r distance away from the center. So to calculate electric field at point P, I will draw my Gaussian surface like a sphere. So here, the calculation is very simple. Means electric field at point P. First case is to calculate electric field at point P, where R, the point radius R is less than capital R. You can write the Gauss law, summation of E dot ds is equal to charge inside by epsilon naught. That is your Gauss law. But there is no charge inside. All the charges outside the surface. So here you can write E ds cos 0. The charge is 0. So E into integration of ds, this is 0. Integration of ds, this is a sphere. So you can write E as E into 4 pi r square is 0. That means your electric field is 0. Electric field is 0. So inside the concentric shell, the electric field is 0.
Sir, the shell is conductor.
The shell is a conductor. It can also be an insulator.
Then also it will be 0.
Then also it will be 0 if it is uniformly distributed. And even if it is non-uniformly distributed, you draw the Gaussian surface, you will find that there is no charge inside, so electric field will be 0. So it doesn't matter if it is conducting or non-conducting, electric field inside will always be 0. If I take a point outside, call it a point Q, and this time my R is like this, small r is like this. So again, you can have the same thing, electric field at point Q, where R is greater than R. So this is very exactly like a point charge. E dot ds. Let us say the total charge, I will not call this point Q because Q is measured for charge. I'll write it as P dash. And charge, total charge distributed on the surface, that is Q. Q on the surface is plus Q. So again, we write E dot ds. It will be, total charge will be Q. It will be Q by epsilon naught. So again, this is a sphere. You will get it as E into 4 pi r square. This Q by epsilon naught. I'm skipping some steps. If you have doubts, you can ask me. I will elaborate it. But it's a sphere. It's just like a point charge. E into 4 pi r square r, 4 pi r square Q by epsilon naught. So electric field comes out to be 1 by 4 pi epsilon naught into Q by r square. So this is when r is less than r. And this is when r is greater than or equal to r.
What is capital Q?
Capital Q is charge on this spherical shell.
Sir, the entire spherical shell or just a
The
part
entire
of it?
spherical shell, yeah. It will be uniformly distributed. So this is charge on the spherical shell, the entire spherical shell. Even if you give it a 1 coulomb of charge, the charge will spread out to each and every point. It will not remain at a single point. So plus Q charges on this charge on this spherical shell. It's good that you're asking questions. Other students, I will request you, miss, if you have any doubts or any thing that is not clear to you, you should ask. That will help other students as well as, of course, yourself. So if R is greater than R, electric field varies as 1 by R square. And if R is less than R, electric field is 0. If you want to plot the graph of electric field versus the distance from the center, electric field versus the distance from the center. So in between, somewhere you will get a point, capital R, that is radius of this spherical shell. And for R less than R, electric field is 0. For R less than R, there will be no electric field. For R greater than R, it varies as 1 by R square. So 1 by R square is it goes like this. As value of R increases, electric field decreases. And this point, your electric field is maximum given by KQ by 4 pi epsilon naught R square. Okay, here the value of electric field at this point will be maximum. That is K into capital Q upon capital R square. At this point, electric field is 1 by 4 pi epsilon naught into Q by R square.
Sir, I didn't understand the graph.
So this graph is between electric field and R. R is distance of the point from the center. If you take R at any point which is less than capital R, here any point you take, R will be less than R. So there is no electric field here. There is no solid line here. But beyond R in this region, R is greater than R. If R is greater than R, any point here, electric field will be given by this formula, K Q by R square. When value of R increases, electric field decreases. But just outside the spherical shell, the value of electric field will be maximum, and that will be given by this equation, 1 by 4 pi epsilon naught Q by capital R square. Capital R is the radius of the spherical shell.
Yes, sir, understood.
Okay. Next, we will understand electric field due to a uniformly charged sphere. Suppose the sphere is uniformly charged. Here it was spherical shell. Next part. This might appear a bit difficult to some students, but let us go through it. So this is electric field due to a uniformly charged sphere. There it was spherical shell. Here it is a whole sphere. So let us say sphere has been given. And the total charge on this sphere is plus Q. Which is uniformly distributed. So all of the charge will be evenly distributed. So charge is evenly distributed over a volume. In that case, we can calculate the volume charge density. So if I calculate the volume charge density, then I would need radius for it. So let us say the radius is capital R. Charge on it is capital Q. The volume charge density written as rho, that will be given by charge divided by the volume, 4 by 3 pi RQ. This will come in handy later in the calculations. Now see, first we'll take the easy portion. Easy portion means I will take a Gaussian surface which is outside the sphere. So I'll take case 1. In case 1, I have to find electric field at a point which is outside the sphere. Let us say at this point, call it P. To find the electric field, you'll draw a Gaussian surface which is outside the sphere. So the Gaussian surface is drawn which has a radius R. Again, I can take a very small surface area here, ds. No, the Gaussian surface is here. So you should take a ds vector here. This will be your ds vector. The surface is like this. And of course, electric field will be radially outwards at each and every point. It will be radially outwards. But what will be its value? That will calculate from the Gauss law. So let us find this value. So summation of E dot ds will be equal to total charge is Q divided by the epsilon naught. And it's a sphere. So again, the same thing will come E into 4 pi R square. See, R is the radius of Gaussian sphere, not the spherical shell. Remember that. So it will be Q by epsilon naught. And simply you're getting the same value that electric field due to a point charge, 1 by 4 pi epsilon naught Q over R square. This was very simple. Any questions on this? This is when point R is outside. I'll write the conditions for it. R should be greater than R. The condition is attached to it. Now we'll go for the second case. This is a bit complicated. This is your charged spherical shell, capital charged sphere, capital R, and charge on this is Q. And I will draw Gaussian sphere. I want to find electric field, let us say somewhere at this point. So my Gaussian sphere will be a sphere inside the charged sphere. So this is your ds vector, and area vector will be along this only. Electric field will be along this, and area vector is also along this. So the integration is pretty easy, that we know. And the radius of this Gaussian sphere is small r. Small r is radius of Gaussian sphere. Okay, go on to calculate the value of the electric field. We'll again use the Gauss law. Summation of E dot ds will be charge inside. Now see, the charge inside is not equal to capital Q. It is some other value. It is not equal to capital Q. Because Gaussian surface is not enclosing all of the charge on the charged sphere. It is not enclosing all of the charge on the charged sphere. So it will be only Q by epsilon naught. How can we find the value of Q? Let us worry about that later. First, let us do the integration part. Again, it's a sphere, so I can directly write E into 4 pi r square. Remember, this is small r. So again, electric field comes out to be Q by 1 by 4 pi epsilon naught into Q by r square. But we want to find it in terms of capital Q. So what we know that is here is the rho remains constant. The value of rho remains constant. What is rho? Charge per unit area, volume. 4 by 3 pi capital R cube. The charge per unit volume remains constant. So for the small q, the volume is 4 by 3 pi r cube. The charge per unit volume remains constant. For the Gaussian surface, if I talk about only the charge that is inside the Gaussian surface, then I have to take only the volume of the Gaussian sphere. This is volume of Gaussian sphere. So if you evaluate this, you will get small q will be equal to capital Q. 4 by 3 pi will get cancelled, and capital Q r cube by small r cube. We can simply put this value over here, and we get the value of electric field as 1 by 4 pi epsilon naught. Instead of Q, I will say capital Q r cube by r cube. R square and one of the cubes will get cancelled. So electric field is 1 by 4 pi epsilon naught into Q by r square into r by r, or Q r by r cube. Remember, r cube is a constant. Capital R cube is a constant. So here see, this is when r is less than r. That is the condition attached to it. So here see, In this case, electric field is directly proportional to R. Here, electric field varied as 1 by R square, small r square, but here electric field is directly proportional to small r. So inside the charged sphere, there is a linear increase, but outside there is a decrease by R square. Any questions? So if I go to draw the graph between the electric field versus R, so up to R, up to capital R, it will be simply a straight line. Because when R is 0, electric field is 0. When R is increasing, it will keep on increasing. So it will simply increase up to value R. After that, it varies as 1 by R square. So as value of R increases, this value will decrease. Now, if you calculate the value of electric field at the surface, then you will simply put R square, instead of small r, you will put capital R. Okay. So at the surface, you'll get the same equation from both the formula. At surface, that is when small r is equal to R, the electric field will be Q by 4 pi epsilon naught R square. So that will be this maximum electric field at this point. At the surface, R is equal to capital R, small r is capital R. So electric field is Q by 4 pi epsilon naught R square. That is the maximum value of electric field at the surface. Any questions? So this question, you have to practice it a few times before you get a hang of it. And once you understand all these cases, you're well adapted in how to apply Gauss theorem. And in your board exams only, these type of questions are asked because they are taken all of the symmetrical cases which are possible. So this was your Gauss law, Gauss theorem. Any questions regarding this? You can note it down and go through it step by step to make sure that you have understood this. There are 3 plates. First is 3 lambda. Second one has 3 infinite linear charges. First line has 3 lambda. Second line has lambda. Third is negatively charged, has minus lambda. At point B, which is x distance away, the electric field is 0. So you have to find the net. You have to find the value of x for which this condition will hold. So here electric field due to first line of charge, that will be 3 lambda. 3 lambda by 2 pi, and it will be 2r plus x into epsilon naught. And for it, it will be lambda by 2 pi into r plus x. For this, it will be lambda by 2 pi, just simply x epsilon naught, and this value should be 0. This is electric field at point B. Now, the lambda by 2 pi epsilon naught can be taken common. What we have remaining is 1 by 2r plus x plus 1 by r plus x minus 1 by x. So this quantity cannot be 0. Only this quantity inside the bracket will be 0. I will solve for it. This will be 2r plus x into r plus x into x.
That will be 3 now.
This here will be 3. Yeah. Now the denominator should not be 0 because x is a positive quantity. So this will not be 0. Only the numerator should be equal to 0. I can form quadratic here. It will be x squared plus this will give me a quadratic equation. To solve for x will be minus b plus minus root b square. B square will be 4r squared plus 4ac because minus sign. So plus 4, 3, 12 to the 24r squared divided by twice of a. 24, 28. So that will be, if you take r common, it will be root 28 minus 2 divided by 6. You can cancel out the 2. It will be r by 3 root of 7 minus 1. The negative, both of them are negative, so that won't be possible. You will ignore the minus 28 thing. So this will be the final answer where the electric field will be 0. So do the calculation yourself. If you are not able to get it, we'll discuss it in the next class. That will be all for today.